Yeah. Good morning, good afternoon, good day wherever you are right now. I'm Moritz Baben, and my colleague Florian Tang and I will show you how easy it is today to get started with process modeling and materials informatics. I will take over the introduction and Florian will perform the demonstration. There's a good reason for that responsibility distribution, because I must admit that I have never learned using Python properly. I have always been a FactSage, including macros, and Excel person. Florian, on the other hand, is a very experienced programmer, fluent in various programming languages, and always praising the benefits of Python for quick scripting and even rather complex programs such as the TDB converter that you know from FactSage and the Covered Optimizer. For both of these programs, he is a developer. In the last year, two things have happened. On the one hand, ChatGPT was around, and it was very clear that it can help in programming. On the other hand, Florian mentioned for our customers, getting started with ChemApp is not easy. But what if we generate a working Python script from Equilib save files? Then users only need to modify the ChemApp script and do not write it from scratch. I love the idea, and I can testify that it works because I am today also a ChemApp for Python user. And today we want to convince you of the same. If you have any question during the webinar, please use the Q&A option and we will answer them at the end of this session. What is the application motivation here is that process modeling and materials informatics require data handling and workflows. That means connecting several calculations, and both of these things are very conveniently done in Python. Today, we use as a demonstrator a case from steel metallurgy, but the concepts are applicable to any process model and materials informatics application. Let me quickly introduce the demonstrator here. We consider a simplified model of the LD converter. This is the steelmaking furnace where a hot metal containing several weight % of carbon is entering, and the carbon should be removed by blowing the oxygen. This is a very exothermal reaction, and the heat, this extra reaction heat can be used to melt scrap or direct reduced iron, for example. So the question that we want to answer today is to determine the optimum oxygen amount to get rid of the carbon without losing the iron. At the same time, we want to determine the heat balance to find out how much scrap we can add. Because the more carbon we will have in the hot metal, the more oxygen we will need to blow, but also the more waste heat we will have that can be used to melt extra scrap. The difficulty is that there is variability in hot metal mass, temperature, and composition that is entering the LD converter. So the approach we will demonstrate today is to use the information about the hot metal, which is here stored in a CSV file, and then first calculate the stream properties of the hot metal. So that means the composition and the enthalpy of the hot metal. And then in a second equilibrium calculation, equilibrate the stream with varying amounts of oxygen, and then identify what is the optimum amount of oxygen that is needed and what is the resulting heat balance. We assume that you are familiar with FactSage and the Equilib module. So Florian, maybe you can quickly introduce how you would calculate the stream properties, so the first step that we need to do in Equilib.
Thank you for the kind introduction, and also hello to everyone attending. It's my pleasure to demonstrate how to work with those products that we just recently added to FactSage. So that was not the intention to thank you already for attending. We start with an Equilib calculation, and we do have obviously something prepared with respect to the webinar. So there is a save file. I will briefly go through the setup of this. It is what Moritz described. We do have a fairly typical hot metal liquid solution that it would be present in an LD converter containing obviously a vast amount of iron and quite some carbon, more carbon than desired for the steel. There's some more alloying elements I'm not going to go into, and at the end we also want to add oxygen. So we're also adding this already, but as a variable amount, so only like that. In the calculation that we want to do, that we're interested in, we are going to look at only the Fe liquid phase from the FTMISC database, which is the hot metal liquid that we're going to use for this calculation. Obviously, this is just a choice you need to make based on what you want to calculate. And then we do set a temperature and a pressure, and this would be for no added oxygen. This will just yield a calculation of that liquid iron liquid hot metal solution. But I want to show this using ChemApp for Python, so I will just use the added functionality that is added in 8.3, which is to export this into a Python script. In the file menu, a new point ChemApp file is available. And in this one, you can choose the export equilib file as ChemApp for Python script, which will open up another conversion program that I'm going to show shortly. But if you do this the first time, after installing 8.3 or after setting up your computer to use FactSage, you first need to download and install ChemApp for Python. This is because we do not ship it along with the FactSage installation packages, because there's a more dynamic installation process going on that is hard to retrofit. I, however, did this already, and I will just now conclude. I'm going to pick this hot metal liquid name for the calculation, and now the conversion program opens up. I'm sorry, because I have a two-screen setup. It's always opening up on the other one. And this is already pre-filled. So we do have the environment that we're using, which I already set up for this webinar. So that has already ChemApp and the equi2py package installed. And it is using the equi file that is generated by FactSage from this calculation, and the database file that has all the selections that we made in the equi file. The output file name I gave already, and I'm going to save this obviously into the webinar directory. There are a few choices you can make here. This is also something that Moritz is, I think, quite aware of, because it does cater to the needs or to the things that you would do in working with Python, that you can either export as a pure Python file or as a Jupyter notebook. We are going to use the Jupyter notebooks. The outcomes obviously should be identical between these two in terms of calculation, but the Jupyter notebooks offer a much higher degree of interactive, interaction surface, basically. There are a few options that you can pick here, but maybe, I don't know, maybe you want to give me some hints, but I would just I would just not use any of these options for now. And now it's just as simple as create ChemApp file to click this button, and then we will receive a respective IPyNB file, which is a Jupyter notebook.
Yeah, I guess when you open the Jupyter notebook, maybe you can very quickly then say what is the difference to a Python script and why the Jupyter notebook is useful. I really like the Jupyter notebook, I must say.
Yeah, sure. So Jupyter notebooks are, like I said, the interactive way to deal with Python. I think it somewhat.
Can you just open it already?
I can just open it, surely. I was about to explain something else. So it is just the script, just as well as the Python script. But since there is a so-called Jupyter kernel in the backend, which kind of keeps the program in a still executed state while it is executing, you can actively manipulate the code while it runs and reruns certain parts of it. It comes in these boxes, and I want to briefly say that this is the demonstrator, and I'm going to use VS Code here. I would suggest to use either PyCharm or VS Code for these type of developments, because they have good support for Python generally, and especially VS Code does very well with Jupyter notebooks. However, you're obviously not limited to this. You could also run this on the command line, but I think the demonstration purposes are much easier to achieve in VS Code. So this is the...
Could you zoom out a bit? Sorry.
In or out?
Out.
Smaller.
Yes. Smaller. Yeah. I think it's better to have some overview.
Okay. Yeah. So as you can see, like from the conversion process, previously we only had the equi file in this directory. You got to believe me that this was just the case. And now the CST file, which is the database file that contains all the selections that were made, is created here, and the IPyNB, just as we did set up in the conversion program. There's also the CSV table that was briefly shown on the the PowerPoint slide, which just contains 5 different compositions. We will use these later, I think. Okay.
Yeah, good. Maybe you can quickly just explain the script before you run it. What are the different parts? What's happening?
Sure. And so the general structure of these Equi2Py generated Python scripts or Jupyter notebooks is always going to be the same. It's a bit of like the determinism of programs anyways, but still it kind of categorizes the different things that needs to be done in a few sections. One of them is the initialization and the general setup, which is really just loading all the Python packages that we need to perform these calculations. On doing so, you will also see that if your ChemApp license is correct, you will see this license message, like it could fail. So if I wasn't having my, like if I haven't had my dongle plugged in right now, it would probably not work. I guess most of the users know by now that with the purchase or with the 8.3 version, you do get 1 year of ChemApp for Python for included for free. After that, this will need to be separately licensed. However, this is all now done in the backend, and I kind of want to point out that this means that the ChemApp session and the Python session now is alive. So now everything we enter will modify what or will have an effect on the results. Then obviously we do need to load the data file. This is similar to the phase selection database selection window in Equilib, where now, because ChemApp is based on these either CST files for the encrypted databases or chemsage.dat file for free and open databases, you always need to have this kind of extract from a FactSage database or have to have acquired the CST file some other way. So I think there's quite a few ways how you can get these. These database files are encoded to your user ID and do have a validity range in terms of like time validity included too. So sometimes they will need to be refreshed. And now this is the two commands that will just load the CST file into the thermodynamic system of ChemApp. I have included this, which is now called CATS. It has nothing to do with hairy animals. It's just an abbreviation for ChemApp thermochemical system. There are quite a few of those abbreviations. I'm just using for brevity. I think they are fairly straightforward to understand, and you will get used to them quite quickly. However, this loads the thermodynamic system, and now this is just set up. That is because my local computer setup has a separate limit for the target calculations. It is good practice to set up the units just as you would do in the Equilib calculation. When you start at the reactants video screen, you would probably set up or check the units. In this case, because you're doing steel metallurgy, we're using tons, which is a bit uncommon to me at least. And then obviously checking Celsius and Kelvin is relatively relevant too. So this is the unit setup, which is just like I said, it's best practice to always include this. And then already we start with the let's say calculation setup, which is now the fixed conditions. We did set the temperature and the pressure as the final conditions in the Equilib window. And obviously this is just generating these kind of calls to the ChemApp stream calculation. We are going to use a stream calculation because in the setup that we chose, we also have two different streams. One is called number one and one is called number two. In ChemApp, which is now following here in ChemApp, you aren't really forced to use number one or number two. Equilib does number one and number two. So I would also suggest to change these in an actual model because it may be more reasonable to do. And then we do create these with the same boundary conditions. There are variable conditions because we use the variable a, but we also set the variable a just to be of value 0. So for now, this is more like a blanket definition. And now these actual calculation parts come up, and this calculation part does iterate over a because the conversion obviously isn't clever enough to ignore that the variable is just set to a single value. It could just be multiple values, but it also allows us to just modify the range and then do multiple calculations. We do have these different phase constituent inputs. This is to, in the current calculation, it's quite important to use the reference phases of the system components so that we do get proper calculation of the reaction enthalpy, because this is a stream calculation. We do need to obviously calculate a delta enthalpy and not a total enthalpy. And then the calculation and the results keeping is done this way. And this would be the end of the script. Do you want me to run this?
Yeah, just yeah, let's run it. Yeah. And I would like to stress that I really like it, that the A loop is already essentially pre-written. It is very easy to modify the A range parameter that you had introduced, and then yeah, you would automatically get everything sorted already in one results object here, the results A. Yeah. And maybe also a quick reminder about the Jupyter notebooks. You're now able to modify one part of these boxes, and then you could just run it again without having to run the whole script again, which I also consider quite reasonable and very convenient. Yeah.
Sure, absolutely. So this is one of the options. So I mean, I did press to run all immediately after I said it. And as you can see, like on the bottom edge of these boxes, it basically takes no time at all to run these. This is like processing time of Python that is captured. So now, obviously, maybe the question is, what do we have here, right? So
yeah, the result is done. Let's have a look at the result.
Exactly. So first, I'm just going to print the result. It is saved into this ordered dictionary because we are iterating over A and we set A to 0.0. I can just access it by that index. You aren't forced to do this in any way, so you can modify your script right away, but I'm just going to do this. And this is now the printout of that result object, which is a rich Python object that can be interacted with in quite a few different ways. We're going to show these two. But you can see that it does say it is a stream calculation result. You do get a summary of what the inputs have been to that calculation in the beginning of this one. So it's giving you the system units, which is, again, it's the tons that are, at least to me, the relevant part about this. It does obviously set the same conditions as we have in Equilib. And now the calculation, just because these are the names, we could have just changed these names too. So then they would be maybe more verbal in a way. And then this is all the setup, and now you can see this is a result, and you see all these extensive properties in the beginning. I guess this is what you were looking for in a way to see whether there is a positive or a negative, ends up being in this case. And then we do get all the different phase amounts and phase constituents. And I guess this is just a separate or different view on the same results as you would get in Equilib in either the FACT format or the ChemApp format or whatever. So that is now the result saved. And I also need to maybe explain briefly. So ChemApp internally is a singleton class. So it means it's not going to be possible to instantiate a calculation. But so you will always have a ChemApp kernel in the backend that is modified by your commands. So you cannot keep multiple of those around. But what you can do is to fetch these result objects, and these are just regular Python objects which can be manipulated and kept, and where you can have multiple from different calculations, and they will all be solid.
Yeah, I also like that now you could just quickly modify the print command here and not print the whole results object, but only print the system enthalpy, right?
Sure. So this is all this is all available as properties and attributes of this class. So this would just be the total system enthalpy. So, but if you were looking, for example, for the results of the gas ideal phase, which I don't really know whether there is valuable information. Yeah, I'm not sure whether there's valuable information, but I know it is in the data file. So that's why I picked this. So you can see that this is dormant in the data file. So obviously there's nothing calculated for this phase. It was maybe a bad example, but I could just as well pick the one phase that we did integrate, and that is now just a slice of the result object, just a piece of that. And it does actually also represent another object which you can act on and which you can copy and keep around for whatever purposes.
Yeah. And you could also now add, I don't know, amount of the phase FELIC, right?
Sure. So if I just dot A would just yield the very close to 100% or 100 tons, which is just like, this is just a rounding error because of the accuracy of the numbers involved.
Yeah. Okay. Thank you. Let's not dive deeper here. Let's go back to the original question, which was, we have lots of stream compositions, or essentially hot metal compositions and hot metal temperatures in the CSV file exactly. Can you show how you would import this and then modify the script?
Sure.
Yeah,
this is very easy. This is one of the advantages of the Python ecosystem that I'm always trying to convince you of, that you can just use.
You managed already, Florian.
You can just use one of these libraries that are available. I guess everybody who has been doing some serious work in the scientific Python area has seen pandas being used, and it's just as easy as using the read CSV it's called, for the hot metal CSV file name, and that will give us after the import, which takes a while, it will just give us this table. I will just, for brevity's sake, I will also set the index of the table to be of the ID, because in this table, apparently you chose an ID. It's not necessarily 0 to 4. So we're just going to use this. And now this table is already fully transformed into a very capable Python object that we can use from now on. But you probably might have me use it too, right?
Oh, right. Yeah.
Okay. So for some, I would just copy the file just as maybe as a not precaution, but maybe to be more indicative. So I will I would just make a copy of this. Maybe for questions, if somebody wants to come back at some point, we can do this. So I will this is a copy of the same file now. And what we want to do is we want to use these two commands. I will just copy them over from here. And we want to interact with the calculation, right? So, and what we are affecting is calculation setup. So I will briefly restructure this a tiny bit in terms of that I'm going to use this data here, and now I'm simply collecting these setup commands to be all in one box. This is really, it's not necessary strictly. I think it's just a bit more maybe easy to look at this. So I'm just going to remove these other boxes so that it's a bit more condensed. So now we do read the data file here. And what you want me to do, I guess, is to now iterate over the different compositions here. So yes. In that case, we are going to add another level to the iteration. And since this we can see the structure on this side of the data frame, so it's fairly easy to transfer this. I will use the index and the, let's call it composition, or maybe in the input data iter rows. So we're going to iterate over the rows, really. And now all these commands need to move inwards one level. And so now we're using unpacking to do this. And I do know these the column headers, so I can just use the variables directly. So it's just one way to do this. There's a lot of different ways how you can interact with these data frames, but this is what I will do now. And now we can set this to be of the content for these respective I may have gone wrong in there. Yeah.
Oh yeah.
Could have been a funny result. We do keep this A around, I guess, for the time being. I will modify the result keeping slightly by adding the second index that we now have for this two-dimensional iteration to be in this. I'm sorry, this is what I need to copy. I'm using copy paste just to spare you all my typing. So we're using this over here, and now the results will be kept. I'm sorry, shouldn't have deleted it here. So now the results will be kept with keys being the tuples of the row that we're calculating at and the oxygen content that we're calculating at. That is obviously also not a structure that you always have to use. It's just the one that we're using here. And I think we also need to modify that this temperature, which is variable for the different calculations, right? So this should go into the iterative part 2, and we just set it to the temperature. So now this would be all the modifications needed to iterate over these different, I'm closing this one for now, I'm moving this away. So now we do have all these variable inputs read from each row of the table. Do you want me to run this?
Yes, please run.
Okay, I will just use the run all button, and it does take now a few 0.1 seconds, so it's not even much. One of the practices that I tend to do is that I would just look at the keys of the dictionary to see whether it all performed. And as you can see, we do have 5 calculations performed for the 4 different indexes, all at the same A, which isn't surprising because that's exactly what we set up, but this is also indicative. And now if you look at one of those, do you have a favorite? Do you want to have a?
I want to know the enthalpy of the second ID.
Second ID?
I'm sorry, third ID. Third ID. I don't care.
So this would be, I need to have a closing bracket. And there is another closing bracket. I'm not good with brackets today. That was a mix-up where the bracket goes. So this is the enthalpy of that one, I guess.
Okay, can you quickly convince me that the enthalpy of the second one is different?
Sure, I think I can.
Yes.
And I'm very happy to report that it is working indeed.
Perfect.
Okay, I'll remove these. They are not relevant anymore.
Yeah. So now we have calculated the enthalpies and the compositions essentially of all the different hot metals that we had in the CSV file. Now would be nice to store them in a stream that we can then load in the next calculation when we add the oxygen with variable amounts, right? So can you quickly store them in a stream object?
Yeah, so this is it's exactly what we need to do if we want to continue with that result in the next calculation, because we cannot keep the state of ChemApp. We can keep these classes, Python classes, to allow this. And I will just add this code down here, which is that we are going to use I call them iron liquid streams. I will use another ordered dictionary. This again, it's not necessarily needed. And now I'm going to iterate over the keys of the results. So I'm using this combined ID and the calculation result in the results dictionary. This would be the table ID and the amount of oxygen, right? Like these are the 2 parts of this key. So I will unpack them. And then I can also then I can already start that for the iron liquid streams, and we're only keeping the IDs. We're because this is only for the only relevant for the table ID, that we now simply use from the calculation result the so-called create stream function. And we call the stream that we want to get out of this iron liquid, which isn't surprising. And we only want to include, I mean, this is now inferred knowledge because we saw the results already. We only want to include the Fe-Lic phase, just to have a small, or like small, but just to have a very specific stream. And running this is very quick. And now you can see that if we look at the, again, the second item, maybe, I'm not sure.
Yeah, okay.
You can now see that this is now a stream state object, and this stream state object has the extensive properties of that phase, of that stream that we defined. I mean, in this case, it's the phases results because we only included this phase, but it could also be if you were just, so you can also filter for elements, you can filter for, you can exclude phases and stuff like that. And then you can see like this is, because again, this is the only phase that is stable in the system, this should be reflecting the actual table values pretty well. I'm not sure whether this is worth investigating, but this, at least the RN content seems to be exactly on point. So, and this is now a stream object, which we can use as an input to a follow-up calculation. If you,
and it also has the same enthalpy, right? I mean, I can see that 1.26 times 10 to the power of 11.
I'm not sure whether
which
I
is
think it
probably
deleted.
the same.
No, it is the same. Yeah.
It's
because again, this is the only phase in that equilibrium.
And also spoiler alert for later. Now we can import this stream as a single line rather than defining all different elements in multiple lines, right? Okay, now step one, we're done. We now have the stream properties of all the hot metals that enter the LD converter. So now it's time probably to go back to Equilib and export a Python script for the actual converter process.
Exactly. This is what's needed now. So we do have the same setup. We are not really interested in this calculation setup as much anymore because we are going to change this. But what we do need to do, why we need to go back, is that I guess now we are going to select. Sorry, that's just a multi-window issue again. So we are going to select all the potentially stable phases, right? So now we're changing the data file, and that is
complex solution thermochemistry.
So now there's quite a lot of phases selected now, and this now means that the CST file is going to be different. And I think you'll want to vary the oxygen content, right?
Yes. So from 0 to 10 tons in steps of 0.2?
Okay, so let's go ahead. This means 51 calculations. We'll manage. So I will just use the same process.
Wait a second. Yeah. The temperature of the LD converter will, let's say we always aim for 1600 degrees Celsius because we have the lower carbon content. We don't want to have the precipitation of solid iron.
Okay.
So we aim for a higher temperature here.
Yeah, I guess like just above the liquidus temperature isn't the right place to be. Okay. On the other hand, we could also change this in the script, or we will likely change the script anyways. So now I'm just going the same way again. I'm exporting this. I would now call this likely LD process because it's closer to being the LD process than just the hot metal liquid. And this one, like this setup hasn't changed. We will receive a new CST file and we will receive a new Python script or Jupyter notebook. And
now please include the example results and post-processing suggestions, but don't remove the last one. It's just many lines,
know about it.
which are probably now a bit confusing.
So I'm just creating
I really like this, what Florian has done, which is that Equi2Py will now automatically give you some example post-processing results or post-processing examples, because always knowing what or how to access the different properties is a little bit difficult. You have to learn a lot of vocabulary of ChemApp essentially. By including these, it will be rather easy to modify, as you will see in a few seconds. Again, you can see with the time step 1033 timestamp,
it's just
this created, is just created now. Good. I guess you can quickly run this, right? And then
I should be able to. So the structure is, as you may have seen or may be able to see by scrolling through, it's very straightforward, the same as previously, so it also makes it easy to understand this. The change temperature also is reflected here. I'm happy it is. And now in this case, we do get an A range that is based on a NumPy A range, which is just another functionality to generate a sequential number list from 0 to 10.2, because it doesn't include the upper bound. This is needed. And now we do have calculation over a varying amount of oxygen added. So this oxygen added is as the gas ideal phase. I'm not sure whether I explained this in the first example. And now since you made me tick the box of post-processing, there are a few examples, and as the developer of EquityPy, I kind of try to have examples that are applicable to many calculations, or that may be a good indicator of what you can do in which way. So they may not be reasonable to your question at hand of the equity calculation, because there's just too many variations going on there. So the first example would be that we're plotting the temperature against the axis of iteration. However, we are iterating over the oxygen amount, so this is now just a flat line. I'm sorry.
Yeah. So we have set temperature to constant 1600, and it's a good result. We have constant 1600, but you can now very easily change it to enthalpy versus A, right?
Sure. So I would just rename the data frame. Not that this is important. The important part would be that in this is now fetching the results items, and again, the X in this case is the calculation result object, and I can just use, just as I did previously show, I can just use the .h to fetch the enthalpy of this one. I will also change the h so that the labels are, no, this got to be E. And now this will just, if I rerun this, and that's Jupyter Notebooks, if I rerun this will now plot the H in J over the added amount of oxygen item.
Yeah, and I like it. I mean, what you see here already is we have one constant slope. That is the regime when we are actually burning the carbon, creating carbon monoxide. And then we have a change in slope as we oxidize the metals. And then we have, again, a different, but again, constant slope. And that is the point when we're oxidizing iron, which is something we don't want to do, obviously. So this crossing would be probably the point where we want to be with a converter process in the end. Yeah, and you can, I don't know, did you want to say something about this, or shall we go to the next example?
I'm perfectly happy. It's very easy to make these also more beautiful, or to just work with these directly in terms of publications.
Yeah, and there are lots of YouTube tutorials and everything on modifying these plots, and
yeah. Okay, yeah. So next example is one example that I put in here just to indicate what I also briefly explained already, how to inquire the result objects with respect to like digging deeper into some specific property. And for this one, it's fairly identical to what we do previously. So we're creating a data frame that fetches some data from the result object, and then we're just using plotting function, and all the rest of the setup is really just for looks. But what we're doing is now, I call this R now, it could have been X, like in the previous box. Now we're going into the phases of the result object. In that phase, we're going into the gas ideal phase. And in that gas ideal phase, we're going into the phase constituents dictionary. And the phase constituents dictionary contains an object that is O2. And for that, I am fetching the activity. This is obviously also documented and accessible if you want to know which properties you can access, but this makes sense. And now in this case, since it already ran, you can see that the oxygen activity rises with increased amount of oxygen, which I think is a correct result. Generally, I'm not sure about the actual curvature, but I think some people may have better knowledge about this.
Yeah, and then you have the plateau when you're in the iron oxide equilibrium. Yeah. Okay.
Yeah.
Very good. Yeah. I guess you could quickly show how to modify, I mean, without ignoring all the labels and everything, but you could just replace gas ideal by Fe-lic and then plot the phase constituent carbon amount, right?
Yeah.
Which is
as you speak, I already have finished this. So since I'm not editing the axis, don't get confused, but this is, I think it makes sense that it's almost reciprocal to the oxygen amount, right?
Exactly, yeah. And we see that we have an amount that is below 10 to the minus 2 for 8 tons of oxygen addition, which makes sense. Yeah, thank you very much. You want to quickly, just very quickly show the last example result?
Yeah, so this is about the phase constituent amounts. Again, it's not about really what we're showing here, but it's about how you can iterate and then actually put multiple of these results into a data frame. And now you have a data frame that contains more than one line of values. Now it doesn't work with a list comprehension anymore, but rather a nested iteration. And now we also have a threshold introduced. This is relatively straightforward, but I want to point out that this iterative object PC here now is a phase constituent state, and it does, like, it's a valid ChemApp object that is in Python, which you can then ask for a lot of these thermodynamic properties and attributes. And this is, yeah, I think it's a very good tool. And you can see that I think around 6 tons of oxygen, some things are happening in the melt, some things are changing.
Yeah. Okay, I see that we are talking too much, Flo. Let's bring these two things together. We now have the first step where we calculated the stream properties. We have the second step where we're calculating the blowing process. Can you show how you would merge these two into a single script, please?
Yeah. So one thing, maybe to make this a bit easier, is I will briefly export this into a Python script. And now this is a bit less visually loose or something. Like, it's a bit more condensed, and where there's also all these comments we could probably just delete. I'm not going to bother too much about this, but this now is the same script as the hot metal liquid as a need to set it phase name on metal liquid. This is the same script now, and since we do want to, I want to just prove that it's the same script by just running the script. Now it will look differently because it does open up a terminal to run the Python interpreter, and then we'll just run this in the end, and then you can see there's the copyright warning in the beginning. Then we did print the phase state of that Fe liquid in between, and at the end I do print the input data. So that's just to conclude that it does the same thing as you would expect. However, now this one needs to be combined with the calculation from the LD process, right? Which we have here. So I will also export this into a Python script. And now to copy this over, I don't need to copy the all the preliminary stuff, but I do need to start where this, I think I need to use this one. This one needs to go there. So we will start with using this other data file just as well in the respective calls. I will copy all these things down. Is this the right one? I'm not sure.
Yes,
yeah, I think it is the right one. So I will copy this into here. And now what we need to do is to revise what we actually did. So since we did read the input data file, we are going to iterate over this one. So we do need to use the, I think I did export this one. No, it's in the.
Oh, but you have the iteration.
I can copy this from
input
up there.
Data. Exactly. Yeah, you have it already.
So this is. I may not have exported the right one. Oh, I did. Oh, it's a multiple hot metal liquids. It's not the other. Yeah. Okay.
Can you just close the wrong one then? The hot metal liquid PY and also yeah.
So I will. I'm sorry. This was a bit.
You shouldn't have done the safety copy.
Yeah, that's always a tricky thing. So I will, and this should have been the multiple. So now this is the one that we're looking for, and at the end of this one, where we do get the streams, we want to attach, and I will use copy paste for this one to just make it a bit more comprehensive. That I'm going to use this part and this part. I will briefly explain this afterwards. So now after this calculation, this is just filling the iron liquid streams dictionary with the resulting streams. And now we do need to load the other CST file, which is the process.cst. We are setting units, we're setting the streams up. And then instead of setting the incoming amount for the phase constituents, we're now going to use the hot metal stream, which is just the objects that we just created, into the iron liquid streams. And we can use the set stream functionality of the stream calculation object of ChemApp, where you can just set a stream. And I want to point out that we are using the amount as it was in the table. So if you remember the table, it did contain the mass in the second part, and I think because it is varying and we are interested in the total enthalpy changes, we do need to scale the stream that comes in to that amount.
The set equilibrium temperature is 1650. I think that you copied wrongly. Can you move it, okay. Make it back to 1600? Yeah, and this now all the data handling that I mean, for me is also hard to understand, but I see
it's a bit
the beauty of the code.
if you want, it's a bit hectic for now, but I will at the end of this Python script, because it's not a it's not just a what do you say, like a Jupyter notebook anymore. I am adding some more code that is really just collecting the data as you wanted it to. So it will collect the total amount that we calculated, the amount of the oxygen added, the amount of the Fe liquid phase, the carbon content, the weight percentages of the carbon content, which is fairly easy to calculate. It's just the ratio of those, and then it's going to calculate or going to collect the delta of the enthalpy, because in this current calculation, delta of the enthalpy is the interesting part, right? We're doing this by, again, iterating over the results and just fetching the respective data. I want to point out that in this case, for the phase, we're looking at the system component of carbon. For the Fe liquid phase, there's just one phase constituent that contains carbon, but if you have more complex phase models or like multiple salt lattices, this can still be a very reasonable thing. And then we're setting, because you kind of indicated that we want to decrease the carbon content to a certain point, we're just using a target value of 0.1, which is 0.1 weight percent of carbon in Fe liquid, to just determine which is now actually the minimum oxygen that we need to add at this point to get to the point of being at the threshold of 0.1. And then also we are emitting the minimum oxygen, like the delta enthalpy at that minimum oxygen. And then we're saving this into the final results.
I think you can delete the last print, right? Oh, anyway.
Yeah, it shouldn't be. this one's not defined. Some things. I was a bit. Yeah, I think it's just because. Why is it not defined?
Probably would have to define it before that loop, don't you? No,
something's not correct, because if you look at this, it says that you have to add at least 10 tons. So something is not correct. This will be hard to debug. I think that it's a bad example, but I will just use one of the.
Yeah, we did the same webinar on Monday.
Exactly, we did the same webinar on Monday. I do need to find which one is the correct one to. If this one was the one that has all the results at the end now. Yeah.
Yes.
So I'm just rerunning. It's the same thing. It's just copied all of this together into a. There's got to be something somewhere which we missed to copy. Sorry for this. Anyway, so you do get the answer that you do have to add. I think this is also with a step size of 0.5. Maybe that is a bit irritating at the current situation. But this is the 5 different results for the different IDs of the hot metal slag, and then you also get different delta H. I will briefly go up and see whether I can modify. I'm pretty sure I can modify this to be with the 0.2. Yeah. So anyway, so this is, we're done with the time. I think it's better to answer some questions now. Yeah, it will take too much time to figure this out. So.
Yeah. I maybe just quickly show that there is the final results.csv that was created.
Oh yeah, sure. This is the final results.csv is
Exactly. So
is this one. So but this is, for me at least, this is nothing to be really reporting about, because it's really the Python table that is a pandas table can just be exported to CSV. You can also export this to Excel or whatever you desire. There's quite a few exports possible. So I know this is very good for you in terms of just being able to continue with work. So yeah, it's fairly easy.
yeah. And also, I mean, don't demonstrate it, but just reporting would be so simple to just change the target temperature of the converter to 650 degrees Celsius. It's changing one line of code, and then you can run everything again, and you will automatically get the new results. Yeah. Okay.
Yeah.
So thank you very much, Florian. Let's use the remaining time to answer some questions. So if you have any question, please use the Q&A option. We have already the first question, which is abbreviations used. Are they available in some PDF files? And yeah, Florian.
Yeah, so there is, yes, they are available. Yes, that is, so with these abbreviations, like they aren't really, you're not forced to use them, right? So at least for the CAEC to do a ChemApp equilibrium calculations, you don't have to do this. You can also just use the class names, which is equilibrium calculation. But on the other hand, there are, in the thermodynamic realm, there are just really a lot of very long names. So quite a few of those can be abbreviated, but I think you will get used to using SCS for system components quite often, and then PHS for phases and PH for phase. So there is a list of these abbreviations. It is also in the online documentation, in which we will send around the link with, I guess.
Exactly,
I don't need to spell it out to you, I think. So there is a list of, I think, like 20 or so fairly reasonable abbreviations that are making your life much easier on the hands, I guess, when typing all of these out.
Exactly. Yeah. So we will send you, after the webinar, we will send you together with a feedback questionnaire, obviously. We will send you a link to the documentation, a link to the installation video, and also a link to a cheat sheet that we created recently in order to quickly see
that also
what's the abbreviation for amount, activity, and everything. Yeah. Okay. Thank you. Next question. Is it necessary to generate new code file each time I want to perform a calculation? I mean, is there a common template for different systems?
I mean, it depends on your ability to manipulate the present script file in your manners. So if you are using the same structure of calculation, you are obviously very free to, for example, just change the temperature of your calculation. But you do need to likely at least create a new database file if you are using another set of incoming amounts or another set of system components or phases or whatever. So that is always required to be done from Equilib. You could not only theoretically, also practically, you can also just create a larger database and then set certain phases to dormant or eliminated in your calculation. That works, but it does come with a bit of a performance penalty at times. And I think the whole question of phase selections and how to include certain phases is already, it's quite tricky in disregarding whether it is in ChemApp or Equilib. So being conscious about that and maybe creating scripts for each of those separate systems that you're calculating will just make you happier in the long term than missing things when manually editing your files.
Yeah, but
other than that, the script can be adapted to quite a few different calculations.
And you've seen that the two different exports that Florian did today both yielded very similar scripts. So the structure is the same with every ChemApp calculation. Essentially, you always need to initialize. You need to load the data file and everything. So yeah, of course, you can use an old script and modify it and extend it as we've also done it here. Yeah. Okay, next one is not really a question. Thank you so much for the seminar, very helpful. Thank you very much for the kind feedback and for joining. Next one. Hi, Moritz, Florian, many thanks for the webinar. Are there any plans to place examples on GitHub eventually and have a community contribute examples? Although license files would not be available, perhaps users will be able to see what others are using, might be worth considering for the time that goes by between user group meetings.
That is a very good suggestion. We have been pondering that question already and have basically pushed that decision to the point where we knew that ChemApp for Python is available in FactSage, and that we do have some, let's say, like the groundwork is now done to allow this. We do have a few examples online, which are on the blog. I know it's not the same as on GitHub, and it doesn't allow to check these out. The license question is tricky, I agree, but there's also ChemApp Lite, and there is not a ChemApp for Python Lite version available as it is for FactSage right now. But since the license is free currently, at least for the time being, it would be fairly straightforward to just put these files online. However, the CST files you need to generate locally because they are tied to your current situation, but it would be fairly straightforward to create some examples using free databases, which is the ChemSage files, which are not tied to your ID.
And I guess we could also just include the exe file that is also automatically saved now with the equi2py script. Sure. And then anybody can recreate the CST file for their user ID. Sounds like a very good
have
idea.
It on
Thank
my
you
plan.
so much.
We will do this relatively soon. I'm very happy that some people are interested in these type of modern workflows.
So yeah, thank you. I would like to ask, how could we approach it using time as a variable? Maybe I can quickly answer that. Time, not really. Possible. I mean, because we're calculating equilibrium properties, so you would have to do the modeling to convert, for example, input amounts into time information. I mean, essentially here we add a constant flow, input flow of oxygen. So the A variable we have, you could consider as kind of a time variable during the blow. And then you could connect several equilibrium calculations if you want to have a more reasonable process simulation using the EERZ model, so the effective equilibrium reaction zone model. Professor Inno Jung has published a couple of papers on those, which I would recommend you to have a look at.
Maybe just to add to this, so the thing is that what we showed is based on what you can do with using equi2py and some minimum additions. Obviously, you are free to put this into a larger framework of Python tools you're using, or chaining calculations, or whatever you do. And you can also wrap calculations into different objects or more complex process descriptions. So I think it's fairly easy to introduce time there, but that is something that is not provided by equi2py, like by the conversion of equilib files. So that's why this wasn't part of that webinar.
Yeah, I can probably also share now publicly that we are working on kinetic models that will make that available finally. So this is in the pipeline. I hope that we will be able to release something next year already, at least some support. Okay, next question. Is it necessary to have FactSage running while using ChemApp? Usually, I think it's once a day. The ChemApp will validate the license with FactSage.
Yeah, it depends on It depends on how your FactSage license validity is checked and how often it is. So if you haven't started FactSage in a while, it will require you to open FactSage. Maybe if you have, for example, swapped dongles, it will require you to start FactSage. But other than that, so on my computer right now, I haven't had FactSage started, and I don't have it started. I did have because of Equilib, but I didn't have it started for weeks on ends. And then I was just using ChemApp. So it does not really need to run, but it needs to be present. And there are some security mechanisms that are being run from the FactSage installation on each time you start ChemApp. So,
okay, let me quickly take the next question. Can we use all functions in FactSage? Is there any limitations? There are a few limitations because ChemApp and FactSage use different, they have different logic. Many things are supported, some are not. We have on our website, we have a list of that. We can also send that information, that link around what is supported. for example, mixed unit input is not directly supported in Equi2Pi. It is supported in ChemApp though. We will probably add that support in the future in Equi2Pi as well. And other things like power equilibrium calculations, Scheil cooling are not directly supported. That is the current state.
Maybe to add to this, because there's a question further down, when doing stepping calculations, will you include something like normal and transitions? So transition calculations are available in ChemApp. It's just that the used syntax and the logic of how to input this is so different from Equilib that it is basically impossible to convert these directly. So there is, so if you use the ChemApp documentation, we have the phase map calculation, and that allows to do transition calculations, but that has a very different setup compared to what Equilib does in transition calculations. So it is fairly hard to translate. So that's why this isn't done now. It could be at some point in the future, but it just doesn't feel worth it from our developer side currently.
We also have That's Great News as a Q&A contribution. I guess that was related to the GitHub repository that we will start soon. Thank you also thank you for bringing it up here. And then we have another question. Could we vary A from the script, or we need to run it from in the Equilib module? Of course, you could just add a variable here. You could replace, for example, the carbon content by a variable B that you introduce here by saying B equals 0 and then a B range equal whatever. And then, sure. That is the point. It is so easy to modify if you read the script, and this is fully independent now from Equilib. So you can modify the script arbitrarily using Python commands, and it is very easy to do that. That is kind of the main point, right?
Yeah, exactly.
Okay, and then the final one we have at the moment, I think probably if there's nothing pressing, we will stop there. Why did you start an Equilib with initial conditions included? In the end, you have calculated a set of different liquid phases, which are used as a basis for the the heat balance values.
That was really just because of the ease of simplicity to not having to load two separate Equi files and to do the setup twice. So that was, it could have been omitted at the start.
Right. I mean, and then there's the difference between the calculations which are in stream mode or that are just point calculations, which are slightly different in the commands. And I consider it easier if we started directly with the stream mode, because otherwise we would have to have a switch in the demonstration. Okay, final question. Can we get a similar Python model for copper smelting? I guess the right answer is please send us a mail to chemapp@factstage.com or to info@GTT-Technologies.de, and then we can discuss this bilaterally. Thank you very much for the question. We are happy to help there also. Okay, and with that, thank you all very, very much for joining, and thank you for the excellent questions in the Q&A. Thank you, Florian, for the very nice demonstration.
Yeah, my pleasure. Thank you for attending.
Yes. Okay. Goodbye, everybody.